Welcome back, Design Junkies, to Mechanical Engineering Made Simple. If the podcast brings you value, help support the show with a like, a follow, or leave a comment below.
Yeah, we've got a really intense one today.
We absolutely do. So I want you to imagine right now that you are the lead engineer on a totally new chemical processing plant. You've just spent massive amounts of your project budget on this towering state-of-the-art industrial centrifugal pump.
I know where this is going.
Right. Your team bolts it down to the concrete pad, they align the laser couplings, they wire up the heavy-duty electricals, and you confidently flip the switch.
Yes.
And for the first 2 hours, it just hums beautifully.
Well, clearly.
But by hour 3, the casing starts vibrating. You start hearing a sound. It sounds like a bucket of loose gravel just being violently tumbled inside the steel volute.
The dreaded gravel sound.
Yeah, exactly. And then by hour 4, the system violently trips the breakers. You open the casing, and your pristine, thousands of dollars stainless steel impeller looks like it has been literally chewed on by a mechanical shark. I mean, it is completely shredded.
It's a terrifying scenario.
It is. And the worst part is, why did that happen? It wasn't a manufacturing defect. It happened because an engineer sitting in a comfortable chair staring at a clean CAD screen missed a single invisible variable in their fluid calculations.
And the craziest part about that is how incredibly common it is. Because when we are in school or when we are just looking at theoretical models, the world is perfect. But the moment you take that design and try to actually build it in physical reality, the universe just starts fighting back.
And that is exactly our mission for today. We are treating this deep dive as a total masterclass, a survival guide for the real world. We've scoured the internet, dug through those late-night panic posts on engineering forums from students cramming for exams, and read the frustrated rants of seasoned pros trying to figure out why their machine parts keep failing on the shop floor.
Yeah, we really pulled a massive stack of intense engineering references for this. We're looking at dense texts covering thermodynamics, fluid mechanics, industrial refrigeration, and rigorous machining and tolerance standards.
But don't worry, we are not going to just read you the textbook.
Yeah.
We are going to distill these rules into the lessons you actually need to survive a brutal design review.
Right.
So whether you are prepping for a final exam, getting ready to defend your system architecture to your lead engineer, or you are literally standing on the shop floor right now, staring at a broken tool, this is for you. We are going to break down the biggest pain points, the most common misconceptions, and the absolute worst traps that engineers fall into.
And we really have to start at the very foundation, because before you can cut a piece of metal on a lathe, or before you can size a pipe or pick out a pump, you have to understand the invisible rules that govern absolutely every physical system in the universe.
Right. We have to talk about energy.
Exactly. Energy.
Which brings us to our first major trap, which is the fundamental misunderstanding of thermodynamics, specifically irreversibility. Now, I know when people hear the word thermodynamics, they instantly picture like a blackboard covered in impossible equations.
Oh, yeah, the flashbacks to junior year.
Exactly. But let's ground this. What is the physical reality we're actually dealing with here?
Well, historically, thermodynamics grew out of the Industrial Revolution. People were building steam engines and just trying to figure out how to get more power out of the coal they were burning. Sadi Carnot famously called it the search for the motive power of fire.
The motive power of fire. I love that phrasing.
It's very poetic, right? But in modern mechanical engineering, thermodynamics is essentially just the study of the relationship between mechanical work, so things moving, shafts spinning, and other forms of energy, like heat. And the trap engineers fall into comes from confusing two very different rules.
Right, the first law and the second law. Let's really unpack the difference here, because this is where the mistakes happen.
So the first law of thermodynamics is the one everyone likes, mostly because it's optimistic. It's the equivalence of work and heat as two forms of energy exchange. Simply put, energy cannot be created or destroyed, it just changes forms. So if you have a closed system, the energy you put into it minus the energy you take out equals the change in the internal energy of the system.
It's a clean, perfectly balanced ledger, just an accounting trick.
Right.
If I put 100 units of heat energy into a boiler, that energy doesn't just vanish, it goes into the steam.
Exactly. It's perfectly accounted for. But the second facet of thermodynamics, and this is the brutal reality where the trap is actually hidden, is the second law. The second law deals with the irreversibility of absolutely all processes that occur in nature.
Okay, stop right there. Irreversibility. That is a very textbook word. What does that actually look like if I'm staring at a physical machine?
Honestly, it looks like waste. Yeah. The second law states that in any real-world process, you generate entropy. Irreversibility, or entropy generation, is this cosmic rule that prevents you from extracting the absolute maximum possible mathematical work from a heat source. It is the exact physical mechanism that prevents us from doing the most with the energy we have.
I always like to think of entropy generation as like a transaction fee.
Oh, that's a good way to put it.
Right.
Mm.
Every single time you make an energy exchange in a system, nature just takes a cut. If you transfer money from a checking account to a savings account in a different bank, the bank might charge you a 2% wiring fee. You can't stop them.
No, you can't.
When you transfer energy from heat to mechanical work in a turbine, nature takes a fee in the form of friction, turbulence, and heat lost to the surrounding air. You can never, ever spend 100% of your energy budget on actual useful work.
That is a phenomenal way to visualize it, a cosmic transaction fee. And this is precisely where the design engineer gets trapped. Because they open up their modeling software, they drop in a component, let's say a gas turbine or an air compressor, and they run the performance calculations assuming ideal mathematically reversible conditions.
Right. They assume the bank isn't going to charge them a fee.
Yes. They assume the bank is generous.
So they do all the math based only on the first law. They look at the energy going in, the energy coming out, and they just assume the difference is pure 100% efficient work.
Yeah, and let's look at the real-world math for an expander or a turbine. If we assume negligible heat transfer to the outside air, under the first law, the work of the turbine is just the mass flow rate of the gas multiplied by the difference between the specific enthalpy at the inlet and the specific enthalpy at the outlet.
With enthalpy basically being a measure of the total heat content in the fluid.
Correct. So the energy balance looks clean, but then physical reality hits, and you have to apply the second law. The math dictates that the entropy generation rate, which we call S-gen, is equal to the mass flow rate multiplied by the difference between the specific entropy at the outlet and the specific entropy at the inlet.
Yeah.
And here is the absolute critical rule. In a real physical system, this value must be greater than 0.
It has to be greater than there. So there is literally no such thing as a zero-fee transaction in nature.
Never. Because of this, the efficiency ratio of any real-world component is drastically impacted. Like, let's look at it from the other direction, a machine that consumes work rather than producing it. Let's look at a compressor.
Okay.
A compressor takes fluid at a low pressure and uses electrical or mechanical work to squeeze it to a high pressure.
Like the loud air compressor sitting in every auto shop in the world.
Exactly. That's the one. If you calculate the efficiency ratio of a real compressor, which is defined as the reversible ideal work divided by the actual physical work required, you are looking at a ratio comparing the change in enthalpy under perfect conditions to the change in enthalpy under real conditions.
Right.
Because of that entropy generation we just talked about, that efficiency ratio is always mathematically and physically less than 1.
Meaning it will never be 100% efficient. You will always have to put more work into it than the theoretical minimum.
Always. And here is the major pain point for the listener trying to design a system. If you size your compressor motor based purely on the reversible ideal mathematical path, what happens when they actually build the factory, bolt the compressor down, and plug it in?
It fails.
It fails miserably. The compressor will either entirely fail to reach the target discharge pressure you promised your client, or in its desperate attempt to reach that pressure, it will draw significantly more power than the electrical grid you specified was designed to handle.
And that means the motor trips, the thermal breakers, the wires overheat, or the system just totally stalls out.
Yeah.
You'd literally go bankrupt on the project because you didn't budget for nature's transaction fee.
Precisely. You are practically forced to oversize your power inputs in the real world. Whether you are dealing with a throttling valve, an adiabatic duct moving air through a building, a supersonic nozzle, or a diffuser, you always have to design your system knowing that S-gen is greater than 0. You have to pad your design to survive reality.
Okay, so that establishes the invisible baseline. We know energy rules everything, and we know we have to pay the entropy tax. But to actually utilize that energy in a factory or a machine, we usually have to move it from point A to point B.
Right.
And in mechanical systems, we almost always move energy using fluids: water, steam, oil, refrigerants. Which brings us to the next massive hurdle engineers face: moving fluid through a system. Because the moment you start sizing pipes, you run headfirst into one of the most maddening mathematical paradoxes in the entire profession.
Oh, yes. Fluid mechanics is where engineering gets incredibly tangible, right? You can see a pipe, you can feel a pump vibrating, but mathematically it is so unforgiving.
Definitely. Before we talk about the paradox, though, let's set the stage with how we figured this stuff out in the first place. Nobody builds a billion-dollar hydroelectric dam or a massive petrochemical pipeline without testing it first.
Of course not.
We test small things in a lab, and then we scale them up. But how do you actually know that water flowing through a 1-inch plastic tube in a university lab is going to behave the exact same way when it is rushing through a 10-foot concrete penstock at a dam?
Well, you don't just guess. You use dimensionless numbers and the concept of dynamic similarity. This is a truly crucial concept for any design engineer. When we want to scale a fluid system, we use dimensionless groups, the most famous of which is probably the Reynolds number.
I know the Reynolds number is critical, but what does it actually represent physically? Like, it's not just a random number, right?
Not at all. Dimensionless numbers are obtained from force ratios. The Reynolds number is physically the ratio of the inertial forces of the fluid. So its momentum, its mass rushing forward divided by the viscous forces.
The viscous forces being the internal friction.
Exactly, the stickiness of the fluid trying to hold it back. You can derive these numbers using dimensional analysis, like the Buckingham pi theorem, or by taking the complex differential equations of motion and energy and writing them in a dimensionless form.
Okay, so how does this actually help us scale a model?
We use dynamic similarity. Dynamic similarity between two geometrically identical systems, say, a tiny 3D printed submarine hull and a massive full-scale nuclear submarine, exists when the appropriate dimensionless groups, like the Reynolds number, are exactly identical for both systems.
Wait, hold on. If the submarine is 100 times bigger, how could the Reynolds number be the exact same?
Because you adjust the other variables. If you make the physical length scale 100 times smaller for the lab model, you might have to test it in a fluid that is much less viscous than seawater, or you might have to run the fluid at a drastically higher velocity to balance the equation.
I see.
Yeah, if you can balance the variables so that the Reynolds number of the lab model matches the Reynolds number of the ocean-going prototype, the fundamental flow regime will be completely identical.
Meaning, if the water flows smoothly over the real submarine, what we call laminar flow, it will flow smoothly over the model. And if it breaks into chaotic, swirling, turbulent flow on the model, we know for an absolute fact it will do the same thing in the real world.
Exactly. It guarantees that the scaling is physically accurate.
Okay, so we know how fluids behave. Now let's talk about containing them. Sizing the pipes. You said earlier there was a mathematical paradox here. Walk us through a typical Tuesday afternoon for a junior engineer who has been asked to size a pipe for a new facility.
Oh man, it is the dreaded pipe sizing iteration loop. It is a classic trap that drives young engineers absolutely crazy because someone fresh out of university is used to having a clean algebra problem.
Right.
They expect to be given a target flow rate, an allowable pressure drop, and then they expect to just plug those two numbers into a formula, hit enter on their calculator, and get the exact required inside diameter of the pipe.
Solve for X. Nice and clean. Why doesn't that work?
Because the real world fights back with a mathematical feedback loop when you try to calculate friction. The core formula we use to relate pressure drop, velocity, and pipe dimensions is the Darcy equation.
Okay, so you set up the Darcy equation. What's the specific problem?
Well, let's say you have a known fluid and a maximum allowed pressure drop, and you need to find the velocity so you can determine your pipe diameter. To find that velocity using the Darcy equation, you absolutely must know the friction factor of the pipe. You just can't solve the equation without it.
Makes sense. Different pipes have different roughness. Like a rusty iron pipe obviously has more friction than a smooth PVC pipe. So you just look up the friction factor in a reference table.
You try to. You go to the famous Moody chart, or you use the Colebrook equation to find your friction factor. But here's the trap. To find the friction factor on that chart, you must input the Reynolds number.
And as we just discussed, the Reynolds number is based on the velocity of the fluid.
Yes. Do you see the loop? To find the friction factor, you need the Reynolds number. To get the Reynolds number, you need the velocity. But to calculate the velocity in the first place, you need the friction factor.
It is a snake eating its own tail.
Exactly. You literally cannot solve the equation directly.
That is infuriating. I mean, if you are a student used to just isolating a variable, that totally breaks your brain. So what do you actually do? You can't just stare at the CAD screen forever. How do you break the loop?
You have to abandon the idea of a direct solution and use an iterative method. You have to make an educated guess, see how wrong you are, and then adjust.
How do you even know what to guess? Like, where do you start?
Typically, you start by assuming a friction factor. A good rule of thumb is to look at the far right side of the Moody chart. You assume that the flow is going to be fully chaotically turbulent inside a rough pipe.
Okay.
In that fully turbulent zone, the friction factor actually levels out and becomes relatively constant regardless of the exact velocity. It gives you a really stable baseline to start from.
Okay, so you pull a reasonable guess for the friction factor out of that fully turbulent zone. Then what?
You take that guessed friction factor and you plug it into your Darcy equation. Now, because you have filled in that blank, you can finally solve the equation and calculate a first-pass velocity. It won't be perfectly accurate, but it gives you a real physical number.
And now that you have a velocity, even a slightly wrong one, you can calculate a real Reynolds number.
Precisely. You use that first-pass velocity to calculate your Reynolds number. Now, you take that actual Reynolds number back to the Moody chart. You look it up, cross-reference it with your pipe roughness, and you find a much better, much more accurate friction factor.
And then you make that second better friction factor, plug it back into the Darcy equation, and calculate a second velocity.
Yes. And you repeat this entire process, iterating in a circle until successive velocities are essentially the same. You loop it until the math stops changing and the numbers finally agree with each other.
That is such a vital lesson. Engineering isn't always about knowing the perfect answer immediately, you know. It's about knowing how to corner the truth by slowly reducing your margin of error.
Exactly.
Are there other ways to solve this if you are sizing a pipe from scratch?
Yeah, a second practical method, if you are strictly sizing a pipe diameter for a given flow rate and pressure drop, is to just guess a standard pipe size, say a 4-inch pipe. You run the math for a 4-inch pipe, calculate the resulting pressure drop, and compare it against your requirement.
And if it fails?
If it creates too much pressure drop, you guess a 6-inch pipe and run the whole thing again. Sometimes, creating a quick plot of pipe diameter on the x-axis and head loss on the y-axis for 3 or 4 trials is the absolute fastest visual way to see exactly where the correct commercial pipe size lies.
All right, so we've iterated our way out of the math trap. We have our pipe diameter. Now we need to actually push the fluid through that pipe. Let's talk about pumps.
Let's do it.
And let's go back to that vivid nightmare scenario I described in the introduction. The $1 million pump that sounded like a gravel mixer and completely destroyed its own impeller in 4 hours. What actually happened there?
That is the ultimate penalty for failing to understand your system data, specifically on the suction side of the pump. But before we diagnose the failure, let's look at what the engineer should have done, because selecting a pump is incredibly unforgiving. If you miss a single parameter, the whole system collapses.
What are the mandatory pieces of data an engineer absolutely must gather before they even open a pump manufacturer's catalog?
According to rigorous system design rules, the very first step is exhaustively gathering your exact fluid system data. First, you need the maximum volumetric flow rate required by the facility, and you must include any expected variations or surge demands.
Okay.
Second, you need the detailed layout and dimensional sizing of the entire pipe network.
And by detailed, we don't just mean it goes from the basement to the roof.
Right.
You need to know every single obstruction.
Every single one. You must account for the friction of every elbow, every T-junction, every isolation valve, every damper, heat exchanger, and filter.
Wow.
Yeah, every single component creates resistance, which we measure as head loss. If you forget to include a massive filter bank in your calculations, your pump will be drastically undersized and won't move the fluid past it.
What else do you need?
You need the exact physical elevation of the pump in the system relative to the fluid source. You need the fluid pressure and temperature at the suction side where the fluid enters the pump. You need the required pressure and temperature at the discharge end. And finally, you have to know the specific fluid characteristics, its density, its viscosity, and whether it contains corrosive chemicals or erosive suspended solids like sand.
Okay, let's focus on the suction side because that is where the monster from the intro lives. You mentioned needing the fluid pressure and temperature at the inlet. This brings up an acronym that strikes fear into the heart of plant operators.
Oh boy.
NPSH, net positive suction head. Explain this physical phenomenon for us.
The destruction of that impeller was caused by cavitation, which is a direct result of ignoring NPSH. Every pump manufacturer will specify a required NPSH for their pump to operate safely. As the system designer, you have to calculate the available NPSH of your physical piping layout. If your available NPSH ever drops below the pump's required NPSH, you trigger a catastrophic physical event.
Let's visualize this. Picture a massive centrifugal pump pulling warm water out of a tank. We all know water boils at 100 degrees Celsius at normal atmospheric pressure. So if the water is only 60 degrees, the engineer thinks they are perfectly safe. But what is physically happening inside the eye of the spinning impeller?
You have to apply Bernoulli's principle. As the fluid is sucked into the fast-spinning eye of the impeller, its velocity increases dramatically. And according to physics, as the velocity of a fluid increases, its local pressure drops.
So the pressure right inside the pump is much lower than the pressure in the room.
Drastically lower. If that local pressure at the eye of the impeller drops below the specific vapor pressure of the water at 60 degrees Celsius, the water physically cannot remain a liquid. It flash boils instantly.
It boils at room temperature just because the pressure was ripped away.
Exactly. Thousands of microscopic vapor bubbles suddenly form in the fluid, but those bubbles don't stay there. The fluid is being pushed outward along the impeller vanes into the volute casing, where the pressure is massively higher.
And what happens to a low-pressure vapor bubble when it is suddenly slammed into a high-pressure zone?
It collapses violently. It doesn't just gently pop, it implodes. And when these microscopic bubbles implode against the metal surface of the impeller, they generate localized shock waves that can hit tens of thousands of psi. It literally blasts microscopic chunks of solid steel out of the impeller.
And millions of those micro-explosions happening every minute is what sounds like a bucket of gravel. It is literally the sound of the pump eating itself alive.
It will destroy a heavy-duty impeller in a matter of hours. That is why NPSH is not a suggestion. It's a hard physical limit.
Unbelievable. Okay, let's assume the engineer got the NPSH right. The pump is running beautifully, it's moving fluid, but a month later, the factory slows down production.
Right.
The operators don't need the maximum flow rate anymore, they only need half. This brings up one of the most frustrating energy-wasting mistakes we see in the field. Let's talk about throttling versus variable speed drives.
This is a tragedy of legacy engineering. Historically, and unfortunately still very often today, if an operator wants to reduce the flow from a centrifugal pump, they simply walk over to a manual throttling valve on the discharge side of the pump and crank it partially closed.
They just physically choke the pipe to force less water through. Why is that so bad?
Because of what it does to the pump curve. When you close that valve, you are artificially creating an immense localized pressure drop, a massive amount of artificial friction. The pump doesn't know you want less flow. The pump just feels a massive wall of resistance pushing back against it. So the pump is forced to work substantially harder, backing up its performance curve to overcome the artificial friction you just created.
So the electrical motor is still drawing huge amounts of current from the grid. It's still spinning at maximum speed, but all that massive electrical energy is just being wasted violently fighting the valve you just closed.
That is exactly what is happening. The energy doesn't disappear. It gets converted into heat and vibration at the valve, wearing out the components and wasting thousands of dollars in electricity.
It sounds identical to getting into your car, pinning the gas pedal to the floor with your right foot so the engine is screaming at the red line, and then using your left foot to mash the brake pedal just so you can drive slowly through a school zone. It is sheer madness.
That analogy is mathematically perfect. You are burning maximum fuel and putting maximum mechanical stress on the entire drivetrain just to go slower. Furthermore, by forcing the pump to operate far off its best efficiency point, you induce extreme radial thrust on the impeller, which physically bends the shaft and destroys the bearings prematurely.
So what should the modern engineer specify instead of a choke valve?
A variable speed drive, or VSD. Sometimes called a variable frequency drive. Instead of artificially choking the flow with a valve, a VSD intercepts the electrical power going to the motor. It changes the electrical frequency, which physically slows down the rotational speed of the motor and the impeller.
You literally just tell the pump to spin slower.
Yes, and the energy savings are staggering because centrifugal pumps obey the affinity laws. The power required by the pump is proportional to the cube of the shaft speed.
Whoa, the cube.
Yes. So if you use a VSD to slow the pump speed down by just 20%, you don't just save 20% of the energy, you drop the power consumption by nearly 50%. It is an incredibly elegant solution that pays for itself in energy savings almost immediately, while also extending the life of the bearings and seals because the machine is under so much less stress.
Okay, so we've covered the energy tax, we've navigated the fluid mechanics loops, and we've stopped our pumps from exploding. But there is a byproduct to all this activity. Moving fluid through pipes generates friction. Machinery doing work generates friction. And friction is heat.
Always.
Removing that heat before it melts our equipment brings us to the next major engineering battleground. We are talking about thermal management, specifically electronics cooling and industrial refrigeration.
Heat is the ultimate enemy of longevity. Whether you are dealing with a microscopic integrated circuit on a motherboard or a massive petrochemical processing column, if you cannot move the heat away faster than it is generated, your system will die.
Let's start on the micro scale. Cooling electronic equipment. When an engineer is looking at a densely packed circuit board that is throwing off a ton of heat, how do they systematically design a way to cool it? It can't just be point a fan at it.
No. It requires a rigorous step-by-step heat balance calculation. According to the standard thermal design methodologies, you start by establishing your physical geometric data. You measure the frontal area where the wire will hit, the flow areas between the components, and the total wetted surface area available for heat transfer.
That's your physical battleground. Then what?
Then you move to the fluid dynamics. You assume an average specific heat for your cooling fluid, usually air, to start the process. You calculate the required temperature-wise of the fluid based on the total heat load the electronics are producing. The formula is essentially the total heat divided by the mass flow rate multiplied by the specific heat.
That gives you your delta T. It tells you that if the air enters at 20 degrees, it has to exit at 40 degrees to carry away the heat.
Correct. But to be mathematically accurate, you then have to evaluate your fluid properties at the average temperature between the inlet and outlet. You have to look up the fluid's dynamic viscosity, its thermal conductivity, and its Prandtl Nano number at that specific temperature.
Because air behaves differently at 20 degrees than it does at 40 degrees. Its density changes. Its ability to carry heat changes.
Exactly. Once you have those precise properties, you calculate your heat transfer coefficient. This usually involves calculating the Reynolds number again to see if the airflow is laminar or turbulent and using friction factors.
And this is usually where an engineer realizes that a bare computer chip doesn't have enough surface area to shed the heat into the air, so they have to add a heat sink, piece of metal with a bunch of fins sticking up. How do they calculate if the fins are actually working?
You calculate the fin efficiency. This involves complex math, often utilizing hyperbolic tangents, to model how heat travels from the hot base of the sink up through the thin metal fin and how much of it successfully convects into the passing air before it reaches the tip. From that, you calculate an overall passage efficiency for the entire heat sink array.
Okay, this brings us to a specific method mentioned in our references that I really want you to clarify. The NTU method, number of transfer units. I know it's heavily used in heat exchanger design. Why do we use it, and what problem does it actually solve for the engineer?
The NTU method is a brilliant mathematical workaround for yet another frustrating loop. Often, when you're designing a cooler, you know the inlet temperature of your hot electronic chip, and you know the inlet temperature of your cold cooling air. But you do not know what the final outlet temperatures will be until you know how effective the heatsink is.
Right. But you can't calculate how effective the heatsink is unless you know the temperature difference.
Exactly. It's the pipe sizing loop all over again. The NTU method bypasses this by focusing on the physical size and thermal capacity of the heat exchanger itself, rather than relying on unknown outlet temperatures. NTU stands for number of transfer units. It is a dimensionless parameter that represents the physical size of the heat exchanger mathematically.
So it's a way of mathematically quantifying how much cooling power does this chunk of aluminum actually have?
Essentially, yes. You form your NTU based on your overall heat transfer coefficient, your surface area, and the heat capacity rates of your fluids. Once you have the NTU, you can use standard charts or effectiveness equations to determine exactly what the actual heat transfer will be, which finally allows you to predict if your electronics will melt or survive. It is a highly structured, incredibly powerful tool.
That is fascinating. Okay, that is pulling heat out of a tiny microchip. Let's scale up. Let's talk about moving massive amounts of heat out of an entire building or an industrial process. Let's talk about refrigeration.
Oh, this is a great topic.
The basic mechanism here is the vapor compression cycle. I'm going to assume our listeners know that heat only flows naturally from hot to cold. So if we want to cool a room on a hot summer day, we have to use mechanical work to force heat to flow backward from cold to hot.
That is the core of refrigeration. We use a refrigerant fluid and we purposely manipulate its pressure to force it to boil and condense at temperatures we dictate.
There are four main components: the compressor, the condenser, the expansion valve, and the evaporator. Let's quickly trace the fluid, but I want to focus on the physical state changes.
Absolutely. We start at the compressor. The compressor pulls in low-pressure, low-temperature refrigerant vapor. It uses raw mechanical power to squeeze that gas. As the pressure skyrockets, the temperature of the gas skyrockets with it. The entire goal of the compressor is to raise the pressure of the refrigerant so high that its saturation temperature, its condensation point, is significantly hotter than the outside air.
Because if the gas is hotter than the outside summer air, the heat will naturally flow out of the gas and into the environment.
Exactly. So that super hot, high-pressure gas is pumped into the condenser, which is the big coil sitting outside your house with a fan on it. As the outside air blows over the coil, the hot gas rejects its heat to the environment. As it loses that heat energy, it physically condenses from a high-pressure gas into a high-pressure liquid.
So now we have a liquid that holds a lot of pressure, but it has dumped its heat. Step 3 is the expansion valve.
The liquid refrigerant is pushed through a tiny restriction, an expansion valve, or a capillary tube. Because it is forced through a tiny hole into a much larger area, the pressure drops instantly and dramatically.
And what happens physically when you drastically drop the pressure on a liquid?
A phenomenon called auto-refrigeration occurs. A small portion of the liquid instantly flash boils into vapor. That boiling process absorbs a massive amount of heat energy from the remaining liquid, which causes the temperature of the fluid to absolutely plummet. It becomes a freezing, cold, low-pressure mixture of liquid and vapor.
Which sets us up for step 4, the evaporator.
Yes, the freezing cold refrigerant flows into the evaporator coil, which is located inside the space you actually want to cool. Because the refrigerant is now much colder than the room air, heat from the room flows into the coil. The liquid refrigerant absorbs that heat, boils completely into a low-pressure vapor, and is sucked back into the compressor to start the cycle all over again.
Beautiful. It is a closed, continuous loop of physics. But here's the pain point. Here's where the ambitious engineer gets themselves into deep, deep trouble. They look at this simple, elegant 4-step cycle, and they try to push it way past its physical limitations.
This is a major catastrophic trap. Let's say a client comes to you and says they need an environmental test chamber cooled down to cryogenic temperature, say minus 100 degrees Celsius. An inexperienced engineer might look at a refrigerant table, find a fluid that boils at minus 100 degrees, and try to build a standard, simple vapor compression cycle with a single massive compressor to achieve that massive pressure differential.
Why doesn't that work? I mean, if the compressor has a big enough motor, why can't it just squeeze the gas hard enough to make the cycle work? What is the physical wall they hit?
The physical wall is the pressure ratio capability of the compressor itself. The simple cycle's lowest practical evaporator temperature is strictly governed by this ratio. Most high-speed reciprocating industrial compressors are absolutely limited to a pressure ratio of 9:1.
9:1, meaning the absolute discharge pressure cannot be more than 9 times higher than the suction pressure entering the compressor.
Correct. For a simple cycle, that mathematical limit usually restricts you to evaporator temperatures of around 2 degrees down to maybe minus 50 degrees Celsius, depending on the refrigerant. If you try to force a single reciprocating compressor to push past that 9:1 ratio, say you try to force a 20:1 ratio to get to minus 100 degrees, the physics just break down violently.
Walk us through the physical failure. What actually breaks inside the machine?
First, extreme heat generation. The act of compressing gas creates heat. If you compress it 20 times over in a single cylinder, the discharge temperature becomes so hot that it physically breaks down the chemical lubricants inside the compressor. The oil literally burns and loses its lubricity.
And metal on metal rubbing at industrial speeds means immediate failure. What else?
Oil foaming. Refrigerants are highly miscible with the lubricating oil. At extreme pressure differentials, especially during startup, the refrigerant flashes violently out of the oil reservoir in the crankcase, causing the oil to turn into a massive foam. The oil pump cannot pump foam, so the bearings run completely dry and seize up.
Wow, so trying to use one compressor to do a massive job just results in a melted, seized piece of scrap metal. If the simple cycle is dead below minus 50 degrees Celsius, how do we actually reach cryogenic temperatures? What is the solution?
If you need to go lower, down to approximately minus 100 degrees Celsius, you graduate to a compound cycle. A compound cycle achieves these temperatures by using 2 or 3 separate compressors arranged in series, all pumping the same common refrigerant.
So instead of one massive machine trying to achieve a 20:1 ratio and melting itself, you have 2 smaller machines. The first one does a safe 4:1 ratio, hands the gas off, and the second one does another 5:1 ratio.
Exactly. It keeps the individual machines safely within their 9:1 application limits. But there's a massive catch. As we said, compressing gas makes it hot. The gas discharging from the first stage compressor is very hot. If you just pipe that hot gas directly into the suction inlet of the second compressor and compress it again,
The final temperature coming out of the second stage will be Astronomically high. You'll still burn the oil and melt the machine.
Yes. So you have to cool the gas between the compression stages. You have to use an intercooler or a flash-type economizer.
How does a flash-type economizer actually work? How do you cool the gas if it's already in the middle of the cycle?
It is just brilliant plumbing. You take a portion of the liquid refrigerant that has already condensed, and you route it through an expansion valve into a middle chamber, the economizer. It drops to the intermediate pressure between the two compressors, and part of it flashes into a freezing cold vapor. You then take the hot discharge gas from the first compressor and you bubble it through, or mix it with, this freezing cold vapor before it enters the second compressor.
Well, that is incredibly clever. You use the refrigerant to cool itself down mid-cycle, so the second compressor gets a nice cool gulp of gas instead of a blast furnace.
Exactly. It protects the second compressor from overheating, and mathematically, it drastically improves the overall thermodynamic efficiency of the entire system.
Okay, but what if you need to go even colder? Let's say you are at a liquid natural gas facility, and you need to hit minus 160 degrees Celsius. What if even a compound cycle fails? Because the specific volume of the refrigerant gas at those extreme low temperatures becomes so massively expanded that your first stage compressor would have to be the size of a house just to move a few pounds of gas.
When you hit those extremes, you abandon the single fluid entirely, and you graduate to the ultimate system, a cascade cycle. A cascade cycle consists of 2, 3, or even more entirely separate refrigeration systems using entirely separate refrigerant fluids linked together thermally.
Separate fluids, why?
Because every refrigerant has a happy zone, a specific range of temperatures and pressures where it performs efficiently without its pressure becoming dangerously high or practically a vacuum. In a cascade system, the cascade condenser, which is a heavily insulated heat exchanger, acts as the evaporator for the high temperature cycle and simultaneously acts as the condenser for the low temperature cycle.
Let me visualize this. You have a high temp loop running, say, propane.
Right.
It's operating at normal pressures and dumping its heat into the outside air. But its evaporator is physically wrapped around the condenser of the low temp loop.
Precisely. So the low temperature loop might be running methane, which boils at incredibly low temperatures. The methane pulls heat out of the natural gas you are trying to liquefy at minus 160 degrees. The methane compressor pumps that gas, but instead of trying to dump that heat into the hot outside air, which would require an impossible pressure, it dumps its heat into the freezing cold propane evaporator.
It passes the thermal baton. The methane operates in its perfect pressure zone, hands the heat to ethylene, which hands it to propane, which hands it to the atmosphere. That is a masterpiece of engineering.
That really is beautiful.
Now, speaking of these refrigerants, methane and propane are obvious names. But when I look through the engineering sources, I see these complex alphanumeric codes everywhere. R12, R134A, R407C. What is the actual logic behind this numbering system?
Well, the chemical names of these engineered fluorocarbons are incredibly cumbersome for everyday use. Try saying 11-in-132 tetrafluoroethane 5 times fast on a busy job site.
I'm not even going to try.
Exactly. So standard numbering systems were devised. The universal standard is the ANSI HRA 34-1992 system. It assigns numbers to hydrocarbons and halocarbons so that the number uniquely and mathematically specifies the exact chemical compound based on its molecular structure specifically, the number of carbon, hydrogen, and fluorine atoms.
And there is a vital safety classification system tied to this too, right? This isn't just about chemistry. It's about not killing the occupants of the building.
Absolutely. The safety groups are paramount. Refrigerants are grouped by 2 critical vectors, toxicity and flammability. Toxicity is rigorously quantified by the threshold limit value, time-weighted average, known as the TLV-TWA.
What does that mean in plain English?
It means if you are locked in a room with a leak, how much of this gas can be in the air before it harms you. If a refrigerant is considered non-toxic in quantities less than 400 parts per million, it earns an A designation. If it is toxic at concentrations less than 400 parts per million, it is designated as a B-class hazard.
So A is relatively safe to breathe in small amounts, and B is highly toxic. What about the flammability vector?
Flammability gets a numerical designation appended to the letter, 1, 2, or 3. Group 1 means the gas is non-flammable under typical conditions. Group 2 is moderately flammable. Group 3 is highly flammable or explosive.
So an A1 classification is the holy grail for a building engineer. It is non-toxic and non-flammable.
Exactly. And for decades, many of the old chlorofluorocarbons, the CFCs, like R11 and R12, were classified as A1. Thermodynamically and safely, they were essentially perfect, incredibly stable refrigerants.
But there was a massive, planet-sized, real-world problem with them.
The environment, yes. Because they were so chemically stable, when they leaked, they drifted all the way up into the stratosphere. There, ultraviolet radiation finally broke them apart, releasing raw chlorine atoms. Those chlorine atoms acted as catalysts, violently destroying the Earth's protective ozone layer.
Which led to the Montreal Protocol, forcing an entire global industry to reinvent its chemistry overnight. We had to transition away from the perfect A1 refrigerants.
It was a massive undertaking. The industry transitioned first to HCFCs, hydrochlorofluorocarbons like R22, as a temporary transitional step because they broke down faster in the lower atmosphere. And now, modern systems use HFCs, hydrofluorocarbons like R134A, which is the direct replacement for R12 in your car's AC. R134A contains 0 chlorine, so its ozone depletion potential is 0, but it completely changed how we have to design the internal seals, oils, and pressures of our cooling systems.
Okay, we have covered an immense amount of ground. We have done the thermodynamic math, we have iteratively sized the pipes, we have managed the cavitation, and we have mastered the heat exchange and the refrigerants. Now we actually have to physically build the machine parts out of solid blocks of metal.
Getting our hands dirty.
Exactly. Which brings us to our next brutal reality check, making it real. Machining minefields.
This is where pure theory crashes violently into the grease and noise of the manufacturing floor. You can design an absolutely perfect, mathematically flawless part in your CAD software, but if you do not fundamentally understand how that geometry is physically cut out of a piece of steel, you will destroy expensive tools, scrap raw materials, and completely blow your project budget.
The core physical interaction of all machining revolves around speeds and feeds. Let's step into the boots of the shop foreman. Explain the physical concept of what is happening at the cutting edge.
Everything in machining, whether on a lathe, a mill, or a drill press, is dictated by 2 primary variables. First, the cutting speed. This is physically how fast the surface of the workpiece is rushing past the sharp edge of the cutting tool, usually measured in surface feet per minute or meters per minute.
So on a lathe, it's how fast the cylinder of metal is spinning. And on a mill, it's how fast the outside edge of the spinning cutter is moving.
Exactly. The second variable is the feed rate. This is the physical distance the tool is forcibly advanced into the material during 1 revolution of the spindle, or over 1 minute of time. It dictates the thickness of the chip being carved off.
And the misconception, the absolute most common and destructive pain point for young engineers and inexperienced machinists, is the simple caveman belief that faster is always better. If I spin the tool faster, I get the part done sooner.
It is the most destructive assumption on the shop floor. Cutting speeds must be drastically and scientifically altered depending on the physical properties of the material. If you are machining a soft metal, like a block of aluminum or a zinc alloy, the material shears easily. You can run the spindle at incredibly high speeds, peel off massive chips, and the tool barely gets warm.
But what happens when that same engineer loads up a billet of tough superalloy or a chunk of austenitic stainless steel, and they try to maintain that same aggressive high-speed approach?
You destroy your tooling almost instantly. The physics change entirely. Let's look at the troubleshooting tables from the standard machining handbooks. Let's visualize a failure. Let's say you are using a high-speed steel drill bit to punch a hole in a block of steel. You bring the quill down, and suddenly, the drill bit splits vertically right up the center web. A loud snap, and the tool is garbage. What physical force caused that?
If the web splits right up the middle, it usually means you fed it into the material way too fast. You applied so much downward mechanical pressure on the point that the steel of the drill couldn't handle the compressive load and fractured. Or it means you had an improper grind on the tip with insufficient lip clearance, so the cutting edge couldn't physically bite into the material and you were just crushing the metal instead of cutting it.
Spot on. It's a thrust failure. Now, what if the drill doesn't split down the middle, but when you pull it out, you notice rapid catastrophic wear and melting on the extreme outer corners of the cutting lips? The outside edges are just gone.
That is a classic speed issue. The outer edge of a drill bit is a part moving at the highest surface speed. If your RPM was too high, the friction at that outer edge generated so much localized heat that it literally surpassed the critical temperature of the tool steel. It drew the temper out of the tool, fundamentally altering its crystalline structure, softening it, and causing it to immediately rub away against the workpiece.
Exactly. You burned the tool. And what about a reamer? A reamer is a delicate tool used to make a hole perfectly round and accurately sized. You run a reamer into a pre-drilled hole, and the shank violently snaps in half.
Again, usually a feed issue. You forced it into the hole too aggressively or the cutting edges were dull. This creates massive rotational friction, which generates twisting torque until the shear stress exceeds the strength of the shank and it snaps.
You have to respect the physical metallurgy of the material. The handbooks have strict warnings for materials that work harden, like austenitic stainless steels.
Explain work hardening. That sounds like a nightmare.
It is. In some alloys, when you subject the metal to physical stress or friction, the crystalline lattice structure of the metal actually deforms and aligns tightly, instantly creating an incredibly hard, localized crust on the surface. If you are milling stainless steel and you feed the tool too slowly, the cutting edge doesn't bite deep enough to get under the crust. It just rubs on the surface.
And the friction of that rubbing instantly work hardens the surface of the part right in front of the tool.
Yes. You literally turn the surface of your part into armor plating. On the very next rotation, your cutting insert slams into that hardened crust and shatters. The rule is absolute. For work-hardening materials, you must maintain a positive, aggressive feed. You must force the tool to bite deep and decisively underneath the hardened layer on every single pass. No rubbing allowed.
Okay, so we have been talking about metals, which behave relatively predictably. But what happens when you throw something completely alien into the CNC machine? What if a client asks you to machine a complex valve body out of a high-performance plastic, like PEEK or Delrin? I imagine because plastics are so much softer than steel, you can just blast right through them with no problems.
That's a classic machining minefield, and it ruins countless parts.
When you were dealing with plastics, particularly thermoplastics, you were fighting a completely different physical property, the modulus of elasticity.
The modulus of elasticity.
Yeah.
That is the measure of how much a material wants to act like a rubber band, how much it flexes under load and then violently bounces back to its original shape when the load is removed.
Precisely. And the modulus of elasticity for plastics is microscopic compared to metals. We are talking 10 to 60 times smaller than steel.
Wow. So it is incredibly resilient and flexible, highly resilient. And this resilience permits massive deflection during machining. As the sharp cutting tool pushes into the plastic wall, the material isn't just shearing away purely and cleanly like a rigid block of cast iron. The physical pressure of the tool actually forces the plastic to flex and bend away from the cutting edge.
So the tool thinks it cut 1/1000th of an inch, but it only cut 1/2,000th because the other half just bent out of the way. And what happens when the tool passes and the pressure is gone?
The material violently bounces back. The elastic recovery is significant. Because of this, a hole that you drilled or tapped might actually physically shrink after the tool is removed from the bore, and the final hole ends up being a smaller diameter than the solid metal tool that just cut it.
It breaks common sense. The hole is smaller than the drill bit.
It happens all the time. Machinists often have to use specifically oversized taps and drills for plastics just to end up with a standard-sized threaded hole after the plastic relaxes. Furthermore, plastics are terrible conductors of heat, but they have a thermal expansion rate 10 times higher than metals.
Oh, I see where this is going.
Yes. If your cutting tool generates friction, the heat doesn't dissipate into the part. It stays localized at the cut. The plastic locally heats up and swells massively in size. You cut the swollen material exactly to your CAD dimension, but when you take the part out of the machine and let it sit on a bench to cool down to room temperature,
it shrinks. And now your highly expensive plastic aerospace part is completely undersized and goes straight into the trash can.
Exactly. You have to use immense amounts of coolant, incredibly sharp, high-rake tools to slice rather than push. And you have to manage heat obsessively.
Let's talk about the cutting tools themselves. There has been a massive paradigm shift in the industry over the last few decades, moving away from old-school high-speed steel HSS to advanced cemented carbide inserts.
Yes, the introduction of carbides revolutionized manufacturing. Carbides are incredibly hard and can handle cutting speeds and temperatures that would instantly melt a high-speed steel tool. But they introduce entirely new physical failure modes that engineers must understand. A common, highly destructive issue with carbide inserts is thermal cracking.
What does a thermal crack look like?
If you look at the cutting edge under a microscope, you will see a series of tiny, parallel cracks running perfectly perpendicular to the cutting edge. Eventually, these cracks intersect, and a chunk of the carbide edge just fritters away, leaving a jagged edge that ruins the surface finish of your part.
Carbide is one of the hardest substances we have. What physical force is strong enough to cause thermal cracks in it?
Extreme, rapid temperature variations, thermal shock. This happens naturally in intermittent machining operations like face milling. Imagine a milling cutter with carbide inserts spinning. The insert smashes into the steel, takes a heavy, glowing hot cut, absorbs massive heat, and then exits the material to spin freely through the ambient air for half a rotation, rapidly cooling down before smashing into the steel again. That rapid expand contract cycle physically tears the crystalline binder of the carbide apart.
And I assume the use of liquid coolant makes this even worse.
It is the biggest culprit. If you have a glowing hot carbide insert buried in a heavy cut, and a sputtering coolant nozzle hits it with a splash of freezing cold water-soluble coolant intermittently, the instantaneous thermal shock will crack it like pouring cold water into a hot glass pan.
So what is the pro tip for the shop floor? How do you cool carbide safely?
The absolute rule of thumb for carbide is it must be all or nothing. You either use a massive, high-pressure, totally continuous flood of coolant that guarantees the insert never gets hot in the first place, or you turn the coolant off entirely, let the insert get glowing hot, and cut dry using compressed air just to clear the chips. Never, ever go in between.
That is an incredibly practical piece of advice. Okay, so you have managed your speeds and feeds, you survived the thermal shock, and you successfully cut the part. The tool survived. Congratulations.
Job done, right?
Not quite. Because you are not done. Does your finished part actually fit with the other part it is supposed to mate with? Welcome to our next module, the ultimate battleground, tolerances and fits. This is the eternal, blood-soaked war between the design engineers sitting in the clean office and the machinists sweating on the shop floor.
It truly is a war, and it is fought over literal thousandths of an inch. To bring some semblance of order to this chaos, the engineering world relies on strict international standards. The ANSI and ISO standards for limits and fits. These massive tables define exactly, mathematically, how two plain cylindrical parts like a steel shaft and a bronze-bearing hole should physically interact.
There are three main classifications of fits. Break them down physically for the listener.
First, you have clearance fits. This is exactly what it sounds like. In a guaranteed clearance fit, the maximum allowable diameter of the shaft is always, mathematically, smaller than the minimum allowable diameter of the hole. There is always a physical gap of air between them.
So the parts will move freely. You use this for running or sliding applications, like a piston and a cylinder or a shaft spinning inside a bushing.
Precisely. You need that clearance space to allow for a film of lubricating oil. What is the second type?
Transition fits. These are a calculated compromise. Depending on the exact manufacturing tolerance achieved on that specific day, the fit might have a tiny bit of clearance, or it might have a tiny bit of interference.
Exactly. It's a statistical overlap. If the machinist cuts the hole slightly on the large side of the tolerance band and cuts the shaft slightly on the small side, it will slide together easily by hand. But if the hole is on the small side and the shaft is on the large side, you might need a light tap with a rubber mallet to seat them together.
Where do you use a transition fit?
You use them when accurate, rigid location is critical, like a locating pin aligning two massive engine blocks. But you still need to be able to disassemble the parts later without destroying them.
And the third type, the permanent one.
Interference fits, also widely known as force fits or shrink fits. In this scenario, the minimum allowable diameter of the shaft is intentionally machined to be mathematically larger than the maximum allowable diameter of the hole.
The peg is literally bigger than the hole, so how do you get them together?
Brute force or thermal manipulation. You either have to put them in a hydraulic arbor press and mechanically crush them together, scoring the metal as they slide. Or, far more elegantly, you use a thermal fit. You freeze the steel shaft in a vat of liquid nitrogen, which physically shrinks its diameter due to thermal contraction. At the same time, you use an induction heater to heat the housing, expanding the hole. You quickly slip the freezing shaft into the hot hole by hand.
And when they both slowly return to room temperature.
The shaft expands, the hole shrinks, and they meet in the middle, locking together with immense, permanent mechanical pressure. They essentially become one solid piece of metal.
Okay, so the standard tables tell us exactly what dimensions to use to achieve these fits. So where is the pain point? How do engineers mess this up so badly?
They commit the cardinal sin of design engineering, over-tolerancing.
Explain the trap.
It happens when a junior engineer is looking at a CAD drawing on a massive monitor where everything looks perfect. They get nervous. They don't want their assembly to be sloppy or fail, so they decide to just slap ridiculously tight, microscopic tolerances on a dimension just to be safe. They think, if I specify that this shaft must be exactly 1 inch plus or minus 1/10,000th of an inch, it will be perfect.
They specify gauge makers' tolerances, the insane submicron tolerances reserved for the master inspection blocks used to calibrate the measurement tools themselves on a standard mass-produced production part. Like putting a 10,000th tolerance on a crude steel bracket that just holds a plastic cover plate.
Exactly. And the real-world consequence of this fear-based engineering is devastating to a company's budget and production schedule. The engineer doesn't realize that there is a direct, unbreakable physical relationship between the allowable tolerance band and the specific machining process required to achieve it.
Let's dive into that physical relationship. It is intimately tied to surface roughness, right? The RA value, roughness average.
Yes, usually measured in micrometers or microinches. No machine's surface is perfectly smooth. Under a microscope, a turned steel shaft looks like the jagged peaks and valleys of the Rocky Mountains.
So if your tolerance band, the allowable variance in the dimension is a tiny 2/10,000ths of an inch, but the physical peaks and valleys of the tool marks left by the lathe are 3/10,000ths of an inch tall.
You physically cannot measure or hold the tolerance. The surface roughness is literally larger than the tolerance band. A micrometer will give you a different reading depending on whether it is resting on a microscopic peak or a valley.
So what does the machinist have to do when an engineer forces a microscopic IT4 or IT5 grade tolerance on a drawing?
The machinist curses the engineer's name, and then they have to move the part to a completely different class of machine tool. They can't just use a standard CNC lathe or a milling machine. Turning and milling leave a relatively rough surface, maybe an RA of 1.6 to 3.2 micrometers. To hit the crazy tolerance, they have to use cylindrical grinding, which takes significantly longer.
And if the tolerance is even tighter than grinding can handle,
Then they have to move to exotic, incredibly slow processes like honing, lapping, or diamond turning. Lapping involves taking the part, applying a loose microscopic diamond abrasive paste, and mechanically rubbing it against a cast iron plate for hours to slowly wear away single microns of material. Furthermore, to measure a tolerance that tight, the part must be soaked in a temperature-controlled metrology lab at exactly 68 degrees Fahrenheit for 24 hours just to stabilize the thermal expansion before it can be inspected.
which takes a part that should have cost $50 to make on a lathe in 5 minutes and turns it into a $5,000 aerospace-grade component that takes 3 days. And if that bracket didn't functionally need that tight tolerance to do its job, the engineer just burned thousands of dollars of the client's money purely out of ignorance.
It is pure wasted money. The absolute golden rule of mechanical design is specify the loosest possible tolerance that still allows the part to function perfectly in the assembly.
Okay, let me play devil's advocate here. We talked about how clearance fits can be sloppy and transition fits are a gamble. If loose fits are a headache and tight tolerances are expensive, why not just avoid the entire headache of things ever rattling apart by making absolutely every single joint in the machine a permanent interference fit? Just press fit the whole machine together so it is an indestructible solid block.
That sounds like a brilliant, rugged solution until you actually try to operate the machine or, worse, repair it. First of all, if you use interference fits where parts are supposed to rotate or slide, the machine simply won't turn. The motor will stall instantly. But even on static, non-moving structural parts, forcing a massive interference fit everywhere causes extreme internal mechanical stress, known as hoop stress, in the surrounding material.
Right, because the hole is constantly violently trying to squeeze the shaft, and the shaft is constantly trying to bruise the hole open.
Exactly. If you have a thin-walled cast iron hub and you smash a massive oversized steel shaft into it, the hoop stress will cause the cast iron hub to physically crack in half.
What about lubrication?
That is the second massive failure point. If there is an interference fit, there is literally zero physical space, no microscopic gap for a lubricating oil film to exist between the parts. If those parts experience any microscopic vibration or movement, the dry metal-on-metal contact will cause them to gall and physically weld themselves together through friction.
And finally, the maintenance nightmare.
Exactly. If an engineer designs a gearbox where every single bearing is heavily press-fit onto the shaft and into the housing, how does the mechanic in the field change a worn-out bearing 10 years later?
They can't.
They absolutely cannot. Future maintenance becomes physically impossible. You won't be able to disassemble the machine with hand tools. You would have to drag a 50-ton hydraulic press out to the job site and risk destroying the expensive shaft and the housing just to push the cheap bearing off. It turns a 1-hour maintenance job into a catastrophic machine replacement.
And that is why the engineering standards exist. You have to follow the charts. You negotiate the fits based on the functional reality of the machine, not on a desire for a solid block of steel. Okay, this has been an incredibly deep dive into the pain points, the thermodynamics, the fluids, the heat, and the machining. Now, we are going to shift gears into our final segment. We are going to answer the absolute top questions the internet has been asking about these specific topics.
I am ready. Let's pull some questions from the listeners.
Question number 1. We see variations of this all the time on industrial engineering forums. With all the incredibly safe A1 classified modern refrigerants available today, why do massive billion-dollar industrial plants still use highly toxic ammonia or highly flammable propane as their primary refrigerants? From the outside, it seems like sheer lunacy to pump thousands of gallons of explosive gas through a factory.
It does seem crazy if your only frame of reference is the small, safe air conditioning unit sitting in your bedroom window. But in heavy, massive scale industry, performance density and operating costs dictate absolutely everything. Let's look at ammonia, known industrially as R717. Yes, it has a Class B toxicity rating, it smells terrible, and it is moderately flammable. But thermodynamically, ammonia is an absolute, unparalleled powerhouse.
What physical property makes it so good that we're willing to risk the toxicity?
It has a massive specific heat, and even more importantly, its latent enthalpy of vaporization is astronomically high. It is typically 6 to 8 times higher than that of the safe, commonly used halocarbon refrigerants like R134A.
Let's translate that. Enthalpy of vaporization. That means the amount of heat energy the fluid physically absorbs when it boils from a liquid state into a gaseous state in the evaporator.
Exactly. Because ammonia absorbs 6 to 8 times more heat energy per pound of fluid when it boils, it makes the entire system incredibly dense and efficient. You can pump significantly less fluid mass, use much smaller diameter steel pipes, use smaller compressors, and still get a massive factory-scale cooling capacity. It also possesses phenomenal thermal conductivity, meaning heat transfers into it very quickly.
So it's cheap, incredibly efficient, and takes up less space. Are there any physical drawbacks besides the safety aspect?
Yes, a massive metallurgical one. In the presence of even trace amounts of water, ammonia becomes highly corrosive to copper and copper alloys like brass. You cannot use standard copper plumbing in an ammonia plant. It will eat right through the walls of the pipe. You must construct the entire system out of heavy carbon steel, stainless steel, or iron.
Fascinating. And what about propane? R290, highly flammable, A3 rating. Literally explosive, why use it?
Propane is incredibly cheap because it is a basic, naturally occurring hydrocarbon. You don't have to synthesize it in a complex chemical lab. But more importantly, it works phenomenally well in industrial environments where a severe flammability hazard already fundamentally exists.
Give me an example.
A massive petrochemical refinery. The entire facility is already processing millions of gallons of explosive oil and natural gas. The entire plant is already electrically zoned for explosive atmospheres with intrinsically safe wiring. By choosing propane as a refrigerant for their cooling towers, they're adding virtually zero additional hazard to the plant. But the refrigerant costs them literal pennies per pound compared to highly engineered chemical fluorocarbons. It is a calculated, highly optimized risk based on the specific constraints of their environment.
That makes total sense. Context is everything. Okay, question 2. This comes from someone studying for their commercial HVAC certification. What exactly is temperature glide? My textbook mentions it regarding modern refrigerants, but I don't understand the physical concept.
Temperature glide. This is a crucial concept that goes directly back to our discussion on the Montreal Protocol and replacing the old CFCs. It involves zeotropic refrigerant mixtures, like R407C.
Break down the word zeotropic.
A pure fluid, like pure water, or a pure single molecule refrigerant, like the old R12, boils at a single, mathematically constant temperature for a given pressure. If you boil a pot of pure water at atmospheric pressure, it boils at exactly 100 degrees Celsius. The water temperature stays at exactly 100 degrees, absorbing heat until the very last drop turns into steam. Only then can the steam get hotter.
It's a flat line on a temperature graph.
Exactly. But zeotropic mixtures, which we had to invent to replace the banned refrigerants, are not single molecules. They're a blended cocktail of 2 or 3 different refrigerants, all mixed together, and all possessing slightly different natural boiling points. Because of this cocktail nature, they do not evaporate or condense at a single flat line temperature. They phase change over a sliding range of temperatures.
Give me a physical example with actual numbers from the tables.
R47C is the perfect example. It is a blend. At a specific constant pressure in the evaporator, the mixture will begin to boil. The first molecules to boil are the ones with the lowest boiling point. We call this starting point the bubble point. Let's say it starts boiling at -44 degrees Celsius, but as it continues to absorb heat and boil, the remaining liquid becomes richer in the components that have higher boiling points.
So the temperature of the boiling liquid actually physically rises as it boils.
Yes, it doesn't finish boiling into a pure vapor until the temperature rises up to, say, -37 degrees Celsius. We call that finishing point the dew point, that 7-degree continuous temperature shift between starting to boil at -44 and finishing boiling at -37 is the temperature glide.
And why does an engineer care? How does that glide mess up a system?
Because it fundamentally changes the physical heat transfer profile inside the heat exchangers. If an engineer designs an evaporator coil, assuming the refrigerant will stay at a freezing -44 degrees across the entire length of the coil, but in reality, the refrigerant warms up to -37 degrees halfway through the pipe because of the glide, the coil will fail to pull enough heat out of the air. The engineer must mathematically account for that sliding temperature delta when sizing the surface area of the heat exchangers.
All right, question 3. Let's go back to the machine shop floor for the final question. I am struggling with grinding operations. How do I know when I absolutely must switch from a regular standard aluminum oxide grinding wheel to a massively expensive diamond grinding wheel?
It all comes down to the fundamental physics of hardness and abrasion. Grinding is not cutting with a sharp blade. It is using microscopic hard rocks embedded in a wheel to plow tiny chips of metal out of the surface. The standard, unbreakable physical rule is the abrasive grains in your grinding wheel must be significantly harder than the material you are trying to cut.
What happens if the material is harder than the wheel?
The wheel won't cut. The abrasive grains will instantly dull, snap off, or just rub helplessly against the workpiece. This generates massive, localized friction and heat, which will burn your part, warp it, and ruin the temper. We call this glazing the wheel.
So when do standard wheels fail?
The handbook is very specific. Standard silicon carbide or aluminum oxide wheels are fantastic for standard tool steels. But if you are assigned to grind cemented carbides, like the cutting inserts we talked about earlier, which are incredibly hard, or if you are grinding specialized super hard ceramic alloys, standard wheels will glaze over instantly. They simply lack the physical hardness to penetrate the carbide matrix.
So that is when you must bring in the diamonds.
That is when you have no choice. You must use a diamond grinding reel. You are using the hardest known physical substance in the universe to abrade a slightly less hard substance. But it is not as simple as just buying a diamond wheel. You have to carefully specify the concentration, which is how densely the diamond dust is packed into the bonding matrix of the wheel. A high concentration holds its shape better, but cuts slower and hotter.
And you mentioned earlier that coolant is a major issue with carbides.
Yeah.
Does that apply to the grinding wheel itself?
Absolutely. You must carefully choose the bonding material of the wheel based on your coolant setup. Resinoid bonded diamond wheels, where the diamonds are held in a hard plastic resin, are often used for dry grinding of carbides. But you have to take extremely light passes to avoid heat buildup that will melt the resin. If you use a tough metal bonded diamond wheel, you almost always must use a massive continuous flood of liquid coolant to keep the wheel from loading up with melted swarf and failing.
What strikes me so profoundly about all these answers, whether we are discussing the physics of using toxic ammonia for a massive refinery, dealing with the sliding temperature glide of a zeotropic refrigerant blend, or mathematically selecting the right diamond concentration for a grinding wheel, is that every single engineering answer always boils down to one fundamental truth. It depends entirely on the physical constraints of your specific environment.
Exactly.
There is no single magic bullet in mechanical engineering. There's no perfect fluid, no perfect material, and no perfect equation that doesn't require a compromise.
That is exactly right. Engineering is the high-stakes art of optimization under constraint. You have to weigh the absolute laws of physics against the project budget, the safety of the operators, the physical limits of the materials, and find the one path that survives reality.
Which brings us to the end of our masterclass. We have covered an immense amount of ground today, and I want to leave you, the listener, with a final overarching concept to mull over as you go back to your CAD screens or walk back out onto the shop floor. From the very beginning of this deep dive, when we talked about the cosmic inevitability of entropy and the irreversibility of the second law of thermodynamics.
The inescapable energy transaction fee.
Right, all the way down to the microscopic sub-micron surface roughness of a milled steel shaft we discussed in the tolerances section. The engineer's job is never,
ever about achieving true mathematical perfection. Perfection is a myth that only exists inside the pages of a textbook.
Engineering is fundamentally about negotiating with nature's physical imperfections.
Exactly. We know, as a matter of physical law, that we will never get 100% energy efficiency out of a gas turbine. We know that we will never achieve a mathematically perfectly smooth surface on a lathe, no matter how sharp the carbide tool is. We know we will never get absolute, flawless dynamic similarity between a lab model and an ocean-going prototype. What we do, instead of chasing perfection, is use our iterative formulas, our dimensionless numbers, our dimensionless scaling, and our rigorous international standards to find the exact, specific allowance we can physically survive with. We calculate exactly how much friction, heat, and imperfection the system can tolerate before it violently fails. And we design our machines to operate safely right up to that chaotic line. That negotiation with reality is the true art of mechanical engineering. If you got something useful out of today's episode, hit follow and drop a like. It helps grow the show and keeps the engineering knowledge flowing.